Hello, I am Roberto Vasquez from the Institute of Astronomy of UNAM in Ensenada. During this occasion, we are going to present the workshop on high dispersion astronomical spectroscopy. In this workshop, we will be showcasing the Mezcal spectrograph, which is utilized at the National Astronomical Observatory for the observation of planetary nebulae. We are going to cover the topics of data acquisition, data reduction, and of course, data analysis. We have high hopes that this workshop will be an enjoyable experience for you and enable you to acquire knowledge about other subjects before diving into the process of data processing. The workshop consists of 3 sessions. In the first one, we are going to introduce what long-slit spectroscopy is. We'll introduce you to the Mezcal spectrometer and learn about observation strategies. Later, we'll do a visual inspection of the data obtained with Mezcal. In the upcoming session, we will proceed with the basic data processing, the preliminary procedures, and subsequently focus on the crucial aspect of obtaining the kinematics, namely the wavelength calibration. Additionally, we will engage in practical exercises to reinforce our understanding. In the previous session, we discussed the analysis, measurements, and determination of speeds. How do we produce position velocity diagrams? And how do we go about making an initial approach to modeling? We are hopeful that if you have any questions, you kindly ask us or make any observations. Your input is greatly appreciated. Well, let's begin initially with what long-slit spectroscopy is and what this spectroscopy enables us to do. In this image, we have a small figure representing the electromagnetic spectrum. So, what exactly is the electromagnetic spectrum and how does it relate to the image? It is nothing more than the representation of how the energy is distributed, that is, how much energy there is for each energy interval. We can utilize the relationship that energy is h and nu, where h is Planck's constant, nu is frequency, or h is Planck's constant, multiplied by the speed of light and divided by the wavelength. We could employ energy intervals, wavelength intervals, or frequency intervals, and we would be discussing the same concept. How is the energy of a celestial object distributed and spread out across different scales of measurement within the context of astronomy and astrophysics? It is what we know as spectrum, and there we are going to base ourselves to understand everything it does. When we discuss the measurements, we will use detectors. Detectors operating in the optical range are generally broadband devices, which means they do not recognize the colors themselves, but rather detect a wide range of wavelengths within the optical spectrum. It is an extremely wide range of wavelengths. There we can observe. Let's observe if I can move the mouse. Here it is. I hope they see my mouse. Yes. Here we can see, for example, a graph representing the absolute quantum efficiency of a detector. The graph covers the visible range from 360 to over 960 nanometers, which is equivalent to 3600 to 9600 angstroms. It shows that the efficiency is quite uniform for some of the detectors. Therefore, the spectrum cannot be directly observed as we do at shorter wavelengths, where the detector's response varies with the photon's energy. To overcome this limitation, we need support from a device called a spectroscope, which is derived from the Greek roots of the word. Spectroscopes have been used throughout history to analyze light and its components. They provide the means to observe the spectrum and understand its characteristics, allowing scientists to study the properties of light and make important discoveries in various fields of science. The spectroscope is an essential tool in the study of light and plays a crucial role in advancing our understanding of the universe. It has been called a spectroscope when it was possible to take photographs, or when it allows us to take photographs, or a spectrometer when it allows us to make measurements. At this moment, solid-state detectors, CCDs, are the two essential elements, as they capture images and photographs, but we can also measure using them due to the presence of pixels, which allow us to determine on a scale. Consequently, our spectroscope serves as both a spectrograph and a spectrometer, providing us with comprehensive analysis capabilities. At present, a different word holds no meaning whatsoever when analyzed using modern spectrometers, which have advanced capabilities. How to separate light. Our main interest is the distribution and quantity of light at each wavelength, and its significance in each color in the end. So, one of the ways we have done it is with filters. If you put a filter on the telescope and take a picture, it doesn't necessarily mean the same thing with the red filter as with the blue filter. However, as these filters have a wide bandwidth, the spectral resolution, which is the discrepancy between two wavelengths, can be either 1000 amps or 2000 amps. So that is actually referred to as photometry. So the process carried out with filters is referred to as photometry. Although we use narrow filters, e.g., here we have the article by Maru Contreras and colleagues in 2010, where we analyzed the planetary nebula NGC 7354, they see in the left column images an Ha image, and in the right column a nitrogen-2 image. We have conducted experiments using grayscale scales, and in fact in the last image, specifically the ones located at the bottom, we have implemented a procedure known as sharp masking, which involves the removal of certain elements through a technique called spatial filtering, also referred to as a form of noise reduction or enhancement, if you will. We remove the brightest emission to focus on the details, and we can see how the H-alpha image and the ionized nitrogen image do not resemble each other, right? I mean, one looks like a barrel, it is very clearly identified, and the other is formed by many knots, which are very well located and very bright. So, images captured using different filters provide us with valuable insights into how the emission of an object is manifested in various colors and across a range of different wavelengths. However, we would still need to calibrate this in flow in order to obtain the numbers. Is that correct? Ultimately, the purpose of the instrument is to determine resolution. Resolution refers to the wavelength difference that I am determining, and it is a crucial concept. When discussing resolution, we are talking about the wavelength between the difference in wavelength that I am determining using the instrument. So, that thing is called resolution. So we can say that photometry achieves resolutions that are lower than 100, while spectroscopy achieves spectral resolutions that are greater than 100. That ultimately has specific instances or scenarios in which this does not work as intended or prove effective. That's why, preferably, what we use is the concept that if you are using a photometer for photometry, and if you use a spectroscope, then it is spectroscopy. So, what would be the technique employed to separate the different colors? One of the methods is specifically the utilization of a prism. What happens in a rainbow? The drops are small prisms that, when they all work together, produce a very beautiful rainbow naturally. Additionally, for instance, in the presence of water in a fountain, sunlight, and a specific positioning, we are able to observe the decomposition of colors as well. But maybe the simplest thing is to get a prism, a small glass container into which, when white light enters, we observe it being broken down into its constituent colors. That is a fundamental method for performing spectroscopy. The other approach involves utilizing a diffraction grating, which is essentially a piece of glass that contains a large number of finely etched lines. Professionals typically use gratings with hundreds of lines per millimeter, allowing for the observation of the diffraction effect and the decomposition of colors into their constituent wavelengths. In the field of professional astronomy, we utilize this type of devices. Similar to discs like CDs, DVDs, or CDs, which are now used less due to streaming. When light hits these discs, they respond with the decomposition of colors. In the end, we have a scratched surface, as depicted in the drawing, with very fine scratches measuring approximately 83 or 0.4 microns separated by 0.74. Streaming has made these discs less popular, but they still showcase a beautiful color decomposition when illuminated, at 1.6 each of the columns. And that is enough for our eyes to perceive that decomposition. So, what is happening? Well, this type of diffraction is called Fraunhofer. Here, we have a slit, and we can see, for example, some parameters that the slit has. The slit plays a crucial role in this phenomenon. It allows light to pass through and creates a pattern of interference. This pattern is what we observe and analyze to understand the diffraction phenomenon in more detail. For instance, the width of the slit, denoted as letter B, is barely perceptible, but in this particular scale provided, it indicates that more B corresponds to a larger value, while less B corresponds to a smaller value. Additionally, we also have the height of the slit, as well as the theta distance, which represents the angular distance relative to the optical axis. So, if we observe this slit from above, and we would be viewing it from this position with the opening located here, the light enters through this point, and if we possess a lens, which is what we have in this case, it will bring us nearer to the screen, allowing us to observe how the rays converge more towards the center, and there are fewer rays that reach the surrounding areas, resulting in a phenomenon known as diffraction. Therefore, according to the notes, it mentions the occurrence of normal incidence on a flat and rectangular slit. A central maximum appears at position z0, z being the linear distance. At z0 is the maximum, and then as we move away, there is a minimum followed by another maximum and a minimum, and then another maximum, all while moving away from that central position in the z direction. These are orders. The letter M would discuss the orders, so the maxima are positioned with this formula depending on the order and the wavelength used for illumination, as well as the size, width of the slit, and the distance between the slit and the screen. These factors determine how the maxima are placed and can be calculated using this little formula. So, in the end, the form of the irradiance, which refers to the distribution of energy of the intensity, which represents the strength of the energy, is this. This is the form that it takes. Here we have a quite burnt image where the central part, then the minimum, then another maximum, and here another minimum appears further away. It would be a type of cut from this one. The cut from this brightness would be this one that is here. And what it shows us is the small formula that we know as a square zinc element. The square root is nothing more than the sine of the angle beta, divided by beta squared. The intensity is equal to a certain value, which we denote as a value, and this value is normalized by dividing it by the initial and maximum values. As we move away from the center, we start to have these small valleys and peaks, which eventually tend to dissipate little by little. That is the formula for calculating the square root and intensity. It is based on the relationship between the sine of beta, beta squared, and the distance from the center, or the diffraction phenomenon according to Fraunhofer. However, what occurs when we have two slits? If we possess a pair of slits, then there is diffraction, but there is also the phenomenon of interference taking place. So let's assume that the maxima of one of the slits, when they come together with another maximum, have a greater intensity, but when they come together with a minimum, then the intensity of that maximum decreases. The final radiance we would have is a kind of thing with two functions. One function is the maximums and minimums of squared sine. The other function is that all those maximums and minimums of squared cosine, and all those, that squared cosine would in turn have an envelope equal to the squared 5. In this case, for example, we see that the formula is altered a little bit. Here we have a 4, and here we have the squared sinc from a while ago. But here we have this squared cosine that is shaping these maximum and minimum variations in a more pronounced manner, with a higher frequency. This higher frequency brings about more intense fluctuations in the radiance. These angles alpha and beta are dependent on k and a and b, and k represents the number of waves. So ultimately, this thing is determined by the wavelength. It will not be the same function, it will not have the same shape, it will not have the same position of the maxima for different orders, greater than 1. It will not be located in the same place for different wavelengths. Well, then what we have is a total of interference and diffraction effects, and that is what we will ultimately see on the screen where we detect everything. In this particular scenario, we possess a light source that ultimately generates a flat wavefront, correct? Is that not indeed the case that we are currently observing? That plane wavefront arrives simultaneously at the two slits, and on the screen we would have precisely the sum of the two effects, interference and diffraction. And what if we have more slits? So if we have more slits, and here we have, for example, a photo of one slit, two slits, three slits, 4, 5, notice how the brightness of the part where the maxima are located starts to decrease each time, and how it is distributed to the higher orders. Then we would have a very similar formula in the sense that we would have seen of beta over beta squared, but on this side where we have cosine squared, we will have this sign of n times alpha over sine of alpha, where n is the number of slits. And obviously when n equals 1, this term is 1, and then we have the original equation. Okay. When we change the number of slits, then this term begins to have significance, and that is why it in some way distributes the brightness in the other orders. Well, and then here we would have, for example, this, right? Here we would have a variation of a square sign. Then here we have a variation, of the sine of n times the argument, right? Sine squared of n alpha. Here we have sine squared of alpha. And here we'll have the quotient of the two, because in the end it's multiplied by alpha, and n is an integer. Then they'll have certain encounter frequencies, and that'll produce this function with these peaks, right? Here they provided the example of n equal to 6, but if we subsequently multiply that by the square of 5, then it is the identical thing. But the location to which it is heading, the maximums will gradually decrease in irradiance on each occasion. So what I was telling you is conveyed by this happy face. It indicates to remember that alpha and beta rely on k, the wave number, which is 2 pi over lambda. So precisely in these angles, alpha and beta is where the dependency on the wavelength is found. Okay. And what does that mean? When it comes to different colors, those maximums that are far from order 0, of course it is the central one, there everyone agrees. But as we increase the value of n, as we increase the order, we will see how the colors separate more. For n equal to 4, notice how wide the lines are. For n equal to 8, they have the same central position, but a smaller width, and for n equal to 24, for example, the lines are quite narrow, which allows me to distinguish them quite well. Which one is the blue, which one is the green, which one is the red of the same order. For example, this would be order 1. So this is what takes place. This is the comparison of what takes place when we make use of more slits, and what takes place with the colors and their respective effects and outcomes. Then it says something else here. It says, note that the angular positions of the maxima depend on the wavelength. Therefore, the maxima for different wavelengths will appear at different angles with respect to the incident radiance. So the fact that they notice in order 1 there is this separation, and in order 2 they are much more separated, can already give us an idea that when we want a high dispersion, we would tend to look for higher orders. Hence, the abundance of slits is beneficial as it allows us to perform spectroscopy, an essential technique for analyzing substance properties through the study of light-matter interaction. We separate the colors in specific orders that we can subsequently utilize to our advantage. So, just to say that we were talking about a grid through which light passes, which would be transmission, but the same thing happens with reflection, that is, with a grid formed by a little mirror. And then we would have what would be the 0 order at the same angle of incidence, and then as we move towards the angle to the left or right, we would have what would be the first order on both sides, second order, etc. Dispersion is the rate of change of wavelength with angular position. The function we have here is the derivative of lambda with respect to theta, representing the rate of change of wavelength with respect to angular position. Due to the small size of theta, the dispersion along a spectrum of a diffraction grating is approximately constant, as theta is generally negligible. For small values of theta, the cosine tends to 1. Here we have it, right? In other words, between m and practically 1, the dispersion varies in different orders proportionally. If we go to an order 2 times larger, we would have 2 times more dispersion, more or less, okay? The resolution when we have a diffraction grating would be given by lambda over lambda. That is, r multiplied by m times n. That is, the order multiplied by the number of slits. Hence, the radiance in zeroth order is entirely useless, but the radiance in a significant order or with a substantial number of gratings will provide us with precisely a greater dispersion of light. For example, it states an Echelle grating in order 100 achieves spectral resolution of 100K. Therefore, let's contemplate the vast array of possibilities that would be at our disposal if we were to have a resolution of 100,000. Another very interesting thing is the angle of blaze. This was discovered in the year 1888 by John William Strutt, where he made the suggestion that a grid could be designed in such a way that instead of the irradiance being in the zeroth order and its surroundings, that maximum irradiance could be moved to different orders. And a few years later, Robert Williams Good successfully managed to engrave grooves in a general manner on a substrate, specifically glass, with the intention of producing blade grids. So basically it is the location of the maxima of each order, where they are going to depend on the specular reflection of the grid. The location of the maximum interference depends on the specular reflection of each face, so we have two planes in the end, the grid plane and the plane of each mirror. By having that angle, we move the maximum brightness towards the desired order. And therefore, by designing the corresponding angle, we can make the brightness go to the desired order, achieving the desired outcome. This control over the angle allows us to manipulate the brightness distribution and customize the visual effect according to our preferences, resulting in a tailored and personalized experience. This is, for instance, a machine for creating stripes. Here we are able to observe a relatively thick piece of glass, and then the scratches are produced at an angle that we are able to design. In the case of Mezcal, from this high dispersion spectrometer, the grating has an angle of 63.5 degrees. It is especially for very high orders. Another intriguing aspect of this situation is that for these exceptionally high orders, the spectrographs with elongated slits, which possess a remarkably large aperture, demonstrate a phenomenon where the position, for instance, of a spectral line originating from a lamp undergoes a displacement or experiences a slight deviation towards longer wavelengths as we move away from the optical axis of the system. This effect is particularly evident in the long-slit spectrographs, which are designed to capture a wide range of wavelengths. It is an interesting observation that highlights the complex behavior of light in such systems. So, we are going to see that very clearly in the spectra of Mezcal. The spectra of the calibration lamp of Mezcal, we will clearly see the curves, and then those curves should not worry us. Here is the shape of these curves, and they are curves that in the end, when we calibrate in wavelength, these curves disappear, so that should not cause us problems. So, what do we anticipate to observe in astronomical objects? We must bear in mind Kirchhoff's laws. When we possess a hot body, like a star, the spectrum we are going to perceive is a continuous spectrum. When we possess a star and surrounding it we possess a gas that is colder than the star, we would experience the absorption of the photons that stimulate the gas in the stellar atmosphere, and we would witness the rainbow but with black lines, and that is known as an absorption spectrum. When we only have the gas, and although it says cold gas here, it is cold with respect to the focus, but we possess an emitting gas. Therefore, taking into account the physical processes that result in its emission, what we perceive are spectral lines indicating that the radiative energy is released at particular wavelengths depending on the characteristics of the gas and its excitation state as well as ionization state, naturally and inevitably. So we commonly refer to it as emission line spectrum or emission spectrum. And here we'll take a short break.